Okay, here we go. Okay, phones away, please. All right, so I want to go through something real quick with you, and then I'll let you work on some things. Okay, so I want to look at similar triangles real quick. There's kind of two assignments that go together coming up. 8.4 is just talking about some properties of similar triangles, not a big deal. 8.5 is what we're going to do is we're going to look at sort of the analogs. Remember we had all the triangle congruence relationships? Well, we want to take a look at the corresponding triangle similarity relationships. Okay, we're going to do the same kind of stuff we did before. Remember we could say, for example, two triangles, we might have said two triangles were congruent based on SAS or something, right? We're going to have some analogous relationships that we can always rely on to prove that triangles are similar. It's 8 point, no, 8.3 is the one I just put up. Yeah.
Like how long ago was just?
Like yesterday during the day, I think. Yeah. Yeah, I can't remember. Maybe. Yeah. I think it was during school yesterday. 8.4 will be up maybe tonight or tomorrow. Okay. So let's take a look at the situation right here. So if we know that we've got triangle BTW, so that's the big one, right? And triangle ETC, and we're told, what does that mean? They're similar. Yeah, they're similar. Good. It makes kind of sense, doesn't it, if you think about if this is a congruent sign and that's a similarity sign, it really makes sense if you think about the definitions, right? We said congruent is same size and shape, right? Well, the size part comes from the equation, or from the equal sign, because all measures are equal. And the shape part comes from the similarity, right? What does similarity mean? Well, just same shape, but not necessarily same size. Okay. All right, so we want to set up some proportionalities to find some things. Well, first of all, what's the measure? What do you know about, for similar polygons, what do you know about all the angles? Equal. The angles are congruent. Their measures are equal, right? So what's going to be the measure of angle TEC?
79.
It's got to be 79, doesn't it? Because angle, would you agree angle TEC corresponds to angle TBW, or angle B, right? Make sense? So they have to be congruent. So that's one thing we know. That's 79. What if we want to find like ET and BE?
Find the scale factor.
Okay, so we've got it good. We've got to find the scale factor. How are we going to do that?
Use the 12 and 4.
Okay, good, good. And we picked the 12 and the 3 because the 12 and the 3 are known lengths of corresponding sides, right? So if we want to say the scale factor of BTW to ETC, now this is kind of important. So the scale factor, because we can define it in two different ways, right? The scale factor BTW, triangle BTW, to triangle ETC, scale factor is what? 4. It's 4 over 1, isn't it? Right? Everybody see that? Okay, because that's the ratio of the corresponding side in this triangle has a length of 12, and in this one has a length of 3. And so it gives us 4 over 1, which is just 4, right? So if we want to solve then for TE, or ET, what's the proportionality that we're going to set out? Let me raise your hand. Help me out here. Because we know that we solve, it's always when we're dealing with similar figures, we solve for unknowns by setting up proportionalities, or say proportions, right? Just solve it. Okay, so Gabe, what are we going to set up then? We're going to say something's equal to something.
Smaller triangle is fourth of the bigger one and the whole thing.
Okay.
TB is 20.
Okay. So 20 over.
1.
Hang on. What's it equal to? What's the other fraction unit? So you're saying like big to small equals, right? Probably.
I way you're doing it.
Okay, what's your way? That's
I'm
fine.
just saying, if you do 20/4, then you find, you would like
Okay,
take it out into parts and then.
I got you.
Like X.
Okay, so you're saying because the scale factor is 4:1, I got you. So you're saying that the big to small ratio is 4:1. And the way we could maybe, another way of setting it up would be to say, okay, we already found the scale factor, so we wouldn't really need to do this, but we could say a ratio of big to small corresponding sides would be 12:3, which you just simplified to 4, which is fine. Would be the same as big to small. Well, 20 corresponds to, BT corresponds to what side in the small triangle? ET, right. Okay. Right? And so what would I do then to solve for ET? Yeah, just cross multiply and divide by 12 probably, right? So we get, if we did that, yeah, 12 times ET equals 60. Divide each side by 12 and ET equals 5, right? Okay, good. And then if I wanted to find BE, Ellie, what am I going to do there if I want to find BE? So I know this one is 5. What's the last kind of small step to find what that is? Yeah, 20 minus 5. Okay, so 15. Good. Okay. Okay, so what about this one? Let's introduce our first triangle similarity relationship, right? We had, remember that it always required 3 things to show that 2 triangles were congruent. Even if we use, and you might say, okay, what about HL and HA? But really, there was an implied other congruence there, and that's the right angle, right? So we didn't ever have to say it because we knew they were right triangles, and right triangle implies that they both got right angles. But we always need 3 things to prove that triangles were congruent. We don't necessarily need that for all cases for similarity statements. What about this one? If I know that those 2 angles are congruent to those 2 angles, we talked about this the other day, what do I get for free? Yeah, the third angle theorem. We know they all have to add up to 180, so we don't even have to explicitly say this, but we know the third angles would also have to be congruent, right?
And they're similar.
And so then they'd have to be similar because all the angles are congruent, right? And that's a property of similarity. So then we don't even need to have that third one because it's always going to work for any triangle. And so what we say then instead is we just have angle-angle similarity. That's bad. So we would simplify this by just saying that's AA similarity. Okay. Does that make sense? Yes. Okay. So if 2 angles in one triangle are congruent to 2 angles in another triangle, the third has to be, so they're definitely similar. Okay. Okay, this is kind of cool. You know this, and we've talked about this in different ways. At the start of the year, we spent a little time talking about, oh, man. Switch the table. So at the start of the year, we talked about how lines have some parameters, right? We said that it's a 2-dimensional object, or a line's a 1-dimensional object. A line requires 1 additional piece of information, so it requires 2 numbers to dial in a line, so to speak, right? We can do that in a number of ways. Usually the 2 numbers that we use are slope and y-intercept. And by controlling those 2 things, I can come up with any conceivable line in a plane, right? There are infinite possibilities, and I could get any one of them by just controlling those 2 numbers, right? And so then an extension of that thinking would be to say that for any one of those lines, each of those numbers are unique. If I've got the line y equals 3x plus 5, what's the y-intercept of that? It doesn't matter how I choose to calculate that. No matter what I do, I'm going to get, for that particular line that we've drawn, the y-intercept will always be 5. What's the slope? 3. It should make no difference which points we use to calculate slope because that is a property of that individual line, right? It's what makes that line, right? So we know that to be true. We know that the slope is going to be the same. It has to be, regardless of which points we use to calculate it. But how could we maybe make an argument here using similar triangles? Right, so what could we do? How could I use these, we've just identified on this red line, we've identified points A, B, C, and D. Okay, and we could construct slope triangles out of any two of those, right? Remember what a slope triangle is. A slope triangle is just a triangle that's built from the run and the rise. So it's always going to be a right triangle with a horizontal leg and a vertical leg, right? So can we come up with an argument here that's going to say that that ratio always has to be the same? What do you think?
I was gonna say, we think if it can be those 2 points in the triangle, it would all be like, they don't have the same ratio, each of their sides would have the same ratio.
Okay, right, and because of what relationship? You're right. Because if I pick, for example, let's say I'm going to make this one the blue triangle. Okay, and let's make this one the red triangle. Okay, we know that this is horizontal and that's horizontal, right? That's vertical and that's vertical. So, keep going. You're on something good here. Kurt. So what can I establish a relationship between the blue and the red triangles?
The bottom line is parallel.
True. Look at the angles. Okay, good. It's similar by angle, isn't it? Because we know that these are both right triangles, or right angles. And it's telling us that those two are congruent, which we knew they had, right? So that means that the red and the blue are similar triangles. Okay, so now craft an argument from that. So we know that they're similar triangles. Our goal here is to show that the slope is the same regardless of which 2 points you use to calculate. So for example, we should get the same slope by using points B and C or by using points A and D. True, right? And we know that, you guys have known this for a while, that slope is a parameter of a line, property of a line, and so it's never going to change. But could we, say we were trying to explain this to your younger brother or sister who maybe doesn't have quite as much abstract knowledge about math, how could we come up with a way of saying, okay, just using that relationship, that similarity relationship, could we show that the slopes have to be the same?
They're the same shape.
Isn't it like a similarity version of CTC or something?
Well, I mean, no, it's not that hard.
Wait, if the other two lines are parallel, isn't the third one parallel too?
Well, we could hypothesize that, but we don't have a theorem yet to tell us for sure. We'd have to prove that. Okay, but what would be, I don't want to tell you, I don't want to give you any more hints.
Well, the line EC and FD are parallel, and a line is coming out of them at the same angle. So wouldn't that, if they're the same angle for both of them, you want that to correspond to.
So you're saying this angle and this angle are the same?
Yeah,
Yeah, true, true.
and since the angle is the same, they have to have the same slope.
Okay, I mean, we can infer that. I even buy that that's pretty logical thinking, but you're trying to explain this to a younger person who doesn't maybe, can't make that connection so much. The angles are a little, and work with angles so much.
Just because like triangle would be bigger.
Well, okay, but what is, let me ask you this. Within the blue triangle, what does slope mean? Again, what's the definition of slope? Rise over run, right? Okay, so then, so we could say rise over run, doesn't the rise correspond to the length of the vertical leg? Does that make sense? And the run corresponds to the length of the horizontal leg, right?
Yeah.
So we could say that, she had more places to write here. So the slope of BC is equal to the ratio of EC, that's the rise, isn't it? The length of EC, over the run, which is BE, right? Okay. What about the other triangle? What's the slope of AD? same idea, right? So which segment represents the rise? Okay, so FD over AF. Okay, so we're saying that the slope is the same though, right? Agreed? So we ought to be able to set those two slopes equal to each other. Agreed? Okay, so we get EC over BE equals FD over AF, right? But we know already that those, you've already proven to me that the blue triangle and the red triangle are congruent, right? Does that make sense? So if we could, so what's a statement using the horizontal and the vertical sides of these two similar triangles? What's a similarity statement, proportionality, that has to be true because they're similar? So like D, what would you say, FD over something. Well, big to small, right? So from similarity, we know that the ratio of FD over EC must equal what? AF over BE, right? AF over BE. That has to be true. Anybody would agree to that, right? Because they're similar triangles. Well, now can I relate? This is pretty cool. Can I relate this ratio? Whoops. This ratio to that one? Yeah, and that's fair game, right? A property of proportions is I can exchange diagonally, right? So if I just exchange diagonally here or here, I'm gonna show that these two are equivalent proportions, aren't they? Right? So we proved it then, right? If I just went here, let's say I just exchanged these diagonally, which is a fair algebraic step, then we started with something known. You already showed me that by angle-angle similarity, the blue triangle and the red triangle are similar, which tells us this has to be true. Big to small equals big to small. Exchange diagonally, and we get there. Well, what is that? That's just the slope of BC being equal to the slope of AB, right? So we showed it. Yeah, it's kind of subtle, but you see what we did? That's pretty cool. I like that. Yeah.
I think the person I was trying to explain this to would be very confused by now.
No, I
It would
disagree with
be.
that. I disagree with that. I think it's, if you just take these step by step, maybe we put 1s and 2s and 3s. I mean, this is stuff that we could string together logically without having to do anything like appealing to, what it means to be parameters of a line. I mean, you have to have some algebra background to understand why it is that slope and, you can dial in a slope and a y-intercept and get any line, and those are properties of the line. We had those discussions, but those were also founded on your understanding of Algebra 1. And that's not something you could just kind of pull out with somebody and expect them to totally get that. But this, if you have a limited understanding, you just know the simple geometry of similarity, and you know what the definition of slope is, we just proved it,
They don't know that.
right?
I don't know that.
Yeah, you do. Yeah, you do. Okay.
That's weird.
So I mean, really, this is stuff like this to me is interesting and important because it's what math does. I mean, math enables you to like weave a path from point A to point B, which we call a proof, that is indisputable because each step along the way we can all agree on, right? Okay. 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 So how could we do this? This was done, by the way, a little bit of the history of this. This was done we sent blimps and balloons over Germany during World War II, and they had these physicists had developed these super bright flash blimps, essentially. They were these big capacitors that they hung from the balloons, and they could charge these things up, and then they could discharge them, and it would be like, you know, when you have a, Joe, would you put that away, please? Why don't you get rid of that, please? Thank you. So, you know when you have a flash attachment and you turn it on and it kind of whines, it, you know, it makes that whining sound, and then you can pulse it and it makes a real bright flash. What that is that's a capacitor. It's charge that's being, these two plates that are next to each other, and there's charge that's being separated between the plates, and then when you want to discharge it, you just bridge that connection, and all the charge just goes through the flash. It really suddenly makes a bright flash. So they built these capacitors that were so powerful that, like, if you held up a piece of paper when they flashed it, the piece of paper would start burning. It would just catch on fire. So but they could make these really, really bright flashes, and so in the middle of the night, even if there were clouds and things, they'd have this camera that was attached to the balloon, and they'd flash these things, and it just would look like some kind of bomb going on. And then they'd go capture the cameras, and they could get these really precise, you know, before satellites and all this stuff, and you get these really precise visuals of exactly what the enemy camps looked like, and it was one of the things that enabled us to kind of win the war. So this is essentially what they did, right? Here's the blimp, and here's the camera, right? Really, all this camera is. Cool problem. So here's the camera. It's just got a hole in the bottom. The light comes through the hole, and it's focused onto the plane of the film, right? It's called a pinhole camera. They needed to be able to determine how big these camps were. Well, the balloons would fly. They'd fly at a designated height based on what the pressure in the balloon was, and they could calculate that. So they knew essentially where these things flew. How could they turn that into, how could they determine how wide the camp was? What could they do? What do you think?
Wait, so each time they got a picture of the full camp, they didn't get only.
Well, they might have been partial, but they needed to know they needed to know a scale to these things to make them useful a lot of times.
Okay.
Because they were taking pictures of like trenches and bunkers and things. So they needed to know what the scale was so they could know where to launch their projectile, you know, et cetera, et cetera. How could we do that? If we can calculate pretty accurately the height of the balloon or the blimp, what is N? Well, N's just the width of the plate of film, right? What is F?
The size of the camera.
Yeah, it's just the focal length of the camera. It's just, and that's not going to change, right? That's the same. You build the camera, and the focal length is what it is. You know what that is. You know how big the film is because you're looking at it, right? You can estimate pretty accurately how high it was, right? So then, how are we going to calculate G, which is this distance right here?
Determine the ratio between.
Yeah, it's just a ratio, isn't it? Right? It's just a big to small ratio. It's a similarity relationship. So we could say the two things that we know the height and the focal length, right? Those are corresponding parts, aren't they? Right? Agreed. The height is, so if here's the height, then there's the focal length. Those are corresponding parts of those two similar triangles, right? And we know, so we could say big to small equals big, which is G, over small. The only thing that's unknown is that. Right? So we could solve for it in terms of all the other numbers that we knew. That make sense? What if you wanted to, what if there's a great big tree, and why are you doing this? I don't know, I'm just really curious. There's this really big tree next to your yard, and you want to know how tall the tree is. Can you come up with a way of finding the height of the tree without, it's one that you should not climb, by the way. It's really a dangerous big tree. So what could you do?
You buy a
Oh,
helicopter.
right here. Daphne, you got an idea.
The shadow on the floor and then, point of the shadow.
Okay, so here's, okay, we don't even have to get that complicated. You could, I mean, there's some things you could maybe do like that too, but if here's our tree. That beautiful tree.
Oh, yeah.
It looks like the ones I saw.
True artist, don't you think?
Couldn't you just, like, supposedly throw a ball up and then, like, time it when it started dropping?
Yeah, you could. You could do something like that. That's one way to do it. That's gonna be a little bit tricky though, because the thing's moving pretty fast, and how do you know you get it just high enough? There's a little bit of air resistance. Is there something else we could do? Let's say you, here's what you have with you. Trying to measure the height of the tree.
You're really tall.
Let's say you have a meter stick with you, and that's about it.
Oh,
What could you do?
Kirk has a good one.
I know what you got. I'm sure you did. What do you got?
You gotta make the shadow of the meter stick and then compare that to
Ah, okay.
the shadow of the tree.
Ah, interesting. Okay. Very good. So there's one thing you could do. We could say, here's the shadow of the tree. So here's the sun up here, and there's where the light is cut off. So there's the length of the shadow, right? Okay, we can measure that. I mean, we could easily take our meter stick and go up and just kind of, get a pretty good estimate of what the length of the shadow is. Here's our meter stick. And we get the same, the light's coming in parallel, right? Since it's coming from the sun, which is 93 million miles away, so that light, there's not much of an angle there, right? It's coming in parallel rays. So there's the same angle, and here's the length of the shadow cast by the meter stick, right? So this is, let's just say that that's 0.7 meters, 70 centimeters, okay? Or let's just do it in centimeters. We'll measure them in centimeters. It's a meter stick, and so this is 70 centimeters, and this is 100 centimeters, right? We know the length of the shadow cast by the tree. We measure that, and let's just say that it works out to be, how about 28 meters? How could I set up a proportion? Okay, so I could do big to small, or small to big, doesn't matter. So 70 centimeters over 28 meters equals over whatever we're going to call it. Call it X. The height of the tree, we'll call it X, right? Okay. And we can set that up and solve it, right? So are the units going to work out? Let's see what happens if I cross multiply or if I exchange diagonally, right? What if I exchange diagonally here? Then I'd get X over 28 meters equals 100 centimeters over 70 centimeters.
280
So what's going to happen? 2,800, you mean? We don't have to though, because look what happens here. If we exchange diagonally, what happens to these units? They cancel because we treat units like variables, right? So when they line up like that, they cancel. And so that tells us something important. It tells us that the ratio of the height to the length of the base is in the ratio 100 over 70 or 10 over 7. It doesn't matter what units you use, right? You see the value of that? And so now if I cross multiply, or I'll just multiply each side by 28 meters. I just put it back. Yeah. Okay, so then I've got X over 28 meters equals, I can cancel a 0, 10 sevenths. All I've got to do is multiply each side through by 28 meters. And what happens here? Well, I get an X, and what do I get over here? I can do some cross canceling. 28 over 7 is 4 over 1, and so I get 40 meters. And the units work out. Right?
How big is the tree?
over 120
40
feet.
meters.
Yeah. That's big, but trees get that big.
So like 40.
Evergreen trees get that big. I mean, there are trees that are, so somebody can Google it, but I think like the biggest redwoods are like over 300 feet high. I mean, they're huge. Okay, does that make sense? What if it were, okay, so now I double dog dare you to figure this one out.
The redwood was 379.
Should we go measure it? Do a little field trip?
Yeah, let's do this.
What's the name of the biggest tree? Isn't it like General something or other? You ever heard of this before in California? Did you find it?
Yeah, I stopped on 379.
379 feet. 379 feet. That's big. Okay, so here's the dilemma now though. We gotta be problem solvers. Here we go. So now let's say this happens on a day when it's real cloudy and there are no shadows.
The tallest tree is called Hyperion.
Oh, really?
Yeah.
Oh, okay, that's good to know.
Is it in California?
Yeah, it's the redwood. It's 379.3 feet tall. Cut the tree down and then measure.
No, we're not gonna cut the tree down. What do we do if it's really cloudy? How could we set this up in a way so we couldn't use the shadows? Is there something else we could do? But I'll give you this. Okay, here's what you have. This time I'm gonna give you one more. I'm gonna give you one additional piece of equipment. It's gonna be problem solvers. I'm gonna give you a mirror. So you've got a meter stick and a mirror, and that's it.
Shine like a light from the mirror on top.
Okay. So once again, here's our situation.
And then now the shadows that like on the top they let it drop.
Okay. What can we do?
Let a mirror go on the floor so
Ah.
as if it was a shadow.
Okay, so how about this? Daphne's got a good idea. What if we put the mirror on the level ground?
How big is the
So,
mirror?
well, say it again?
Does it matter how big the mirror is?
Not really. It could be a small one. But we put the mirror on the ground,
The mirror put together is the mirror.
so it's gonna look like.
Shows something pretty cute anyways.
Okay, and so here you're standing. There's your eyeball, and so when you line this up, so that you can look down and you see the reflection from the mirror, you see where you can place the mirror, where the top of the meter stick and the top of the tree line up. See, you see how that could work, right? Then you know that that light ray is coming down just like that, right? Now look what we got. We've got two similar triangles again, don't we? Right? We've got this little triangle, which we're gonna make our green triangle. And then we got the big triangle, which is the red triangle. And as long as the meter stick is vertical, which we can do, right? Then we know that those are similar triangles, we can do the same trick, right? You never know what you might have to do this yet.
What if the tree's at an angle?
If the tree's at an angle, it doesn't matter because then we're still, if the tree were leaning over, let's say the tree were, I'll show you. It's still gonna work because we're trying to find the height, right? That's all we're trying to do. How tall it is above the ground. So even if the tree were leaning over, whoops, at some kind of,
Well, you just have to put a meter stick.
so the tree's doing this, doesn't matter. This is still the height of the tree though, right?
Yeah.
Okay. All right. Question?
Why is
I don't know. There's
What if the
a
tree,
farm
what
accident.
if the tree was so tall and you had to stand back far enough that the earth's slope would be?
That's a pretty big tree. That could cause problems. Yeah, you may. You bet.
what if we go
37.
Okay.
What if you're strapped in a canyon, you have to figure out how high the walls are. So when you know how much.
What if you're trapped? You know they're pretty
What if you
high.
have no roller?
You're
You have
stuck
to
in
make
it.
the wall make more of an extra.
Why would you not want to make extra?
just because it breaks?
I know, like, I mean, it's so much. What's that?
6 minutes is enough.
Can we just do this tomorrow? A lawyer in court.
Okay, what do you think? I want to see what you come up with here. I got one other puzzler for you. What do you think the other ways of proving? Can you come up with 2 other ways, relationships for proving triangles are similar? So we have angle, angle. Can you come up with a couple others?
Angle side.
Anything we learned when we were learning triangles, apparently the first semester.
Okay, but they're different, right? So if you incorporate sides into it, which you're going to have to, if you incorporate sides into a similarity relationship, are the sides congruent?
No.
No. What would it be?
Proportional.
Okay. Right. So I want to know some ways then. See if you can come up with 2 ways while I take roll that would work. And I'll give you, here's the hint I'll give you. Each of these 2 ways involves at least 2 S's. Okay? And that's it. That's all I'm telling you. And they all involve 3 letters, I'll tell you that.
Angle, side, side.
How many are there?
I want you to come up with 2. Without Googling anything. Luke, Katie. Cassie.
Like, I was just wondering how that started. Yeah, I don't think like how this happened. Really? Wait, we're trying to show.
Oh, this was weighted by like 200 dollars. I was winning at 600 dollars. Yes.
And I didn't start with the I didn't wait. Pretty good before things.
No, Jesse? No?
I still think this is the best play ever.
I'm so serious. Marvel is weird.
I'm mad at you guys. You guys are copying all of them. Yeah, I know.
Okay, what do you think? Any suggestions?
Side, side, side.
Side angle, side. Let's look at what that would look like.
Is this a sassy?
So let's say we knew that this was 5, and that was 2, and that was 10, and that was 4, and those angles were congruent. That works, doesn't it? That works. That works, because if this angle is congruent, then, how we can prove this without trig? Everybody come up with an explanation for why that has to be the case?
Yes, I do.
Because like these are thing are proportional.
Angle, side, side work.
And in 2. Well, it would have to be 2 horizontal and 1
Oh,
Okay.
It's like
because since those 2 angles are congruent, the third side can't be any bigger or smaller than that big proportional.
Okay, right. So you can kind of picture this. If I were to take this, side and I were just to pull it away, right? So it maintained the same slope, then aren't these 2 always going to retain the same proportions, right? And so that's really all I'm doing is I'm just pulling this back. It's like these lines go forever. So where is this third piece going to be? If we pull this thing back further, it eventually looks like this. So that's one that works. What about side, side, side? By definition, that has to work, doesn't it? right? If I know that this is 5 and that's 2, and let's say this is 4 and that's 8, for sure we got it, right? Because we know if all 3 of those sides are proportional, that's similarity, right? Okay. All right.
All right.
Good place to end.
Also,